Thanks for the introduction. Hi, everyone. My name is Minh. Today, I will talk about the evolution of push at Uber. At Uber, we strive really hard to bridge the gap between the digital and the physical worlds. Right? So even in the very first version of our application, our users have enjoyed the magical moment when they open the app and they see all the cars around them moving in real time. But behind the scene, so to the user, we have always been a real-time experience, right? But behind the scene, the technical detail of how it happened actually have changed a lot over time. Some of the changes happen because we grow as a business. We have more users, we have more developers, we have more features, and we have to build better technology to support that growth. But some of the changes happen purely because we want to provide an even better experience, a more instant experience to our user. Today, I will talk about the lesson that we learned along the way of building such a system. And hopefully, when it's time for you or the company to develop a similar real-time system, you can apply some of the learning that we talk about here. So first of all, in order to move through the rest of this talk, we have to discuss a very simplified model of the Uber application. So on the left-hand side here, you see the UI of the Uber application. At the very top is a destination entry, which is the very first UI element that our users see when they open the app. In the middle is all the cars around that user, and these cars moving around. And we show about up to 8 cars nearby to you. At the top is the list of succession. So the succession can be place of interest nearby. It can be in event from the calendars. It can be destination that you've been to in the past. And the succession is context aware, so depend on the time and location, it can show you different lists of successions. Also, it's personalized, so depend on the past experience, depends on the places that you've been to in the past. It might show some historical destination here as well. At the bottom is the feed. The feed is a single communication channel in the app. Similar to succession, the feed is also context aware, so depends on time and location. The feed can show different contents. The difference of the feed is that it actually can aggregate data from multiple sources and show the data in here. So with that in mind, now we're ready to dive into some some schemes. So the very first scheme and or architecture that we have at Uber, we call Ping, which serves the very initial Uber application. So Ping is a very simple scheme. How it works is that every 4 seconds, the client actually sends a request, contain its context or location to the server. And the server sends back everything about the state of the world. All right. So in this case, it sends back like the list of succession at the top. It sends back like all the nearby cars. It sends back like the feed at the bottom. And because the server sends back every single thing every time, we actually don't need any client to persist anything at all. We was able to survive without any client persistence for years using this exact scheme. Now, the benefit of using such scheme is that it's very simple, right? In fact, it is one of the simplest schemes that you can, or architecture that you can deploy to do a real-time system. First of all, like I mentioned, you don't need any persistence. So there is no data schema to worry about. There's no data migration to worry about. There is no chances for database corruption to happen. The second thing to make it simple is that you don't have to worry about synchronization. Right. So because all the data come in at once, everything is synchronized automatically. The second benefit is that it allows for you to do extremely fast iteration. And this is a very nice benefit when you are a small, scrappy startup. Because if you want to launch a new feature, you can easily add a new data to ping, and then that data instantly become available on the other side, on the client side, and you can use that to develop a new feature right away. The biggest drawback of this come in terms of performance. Because we have to send every single data every single time to the client, a lot of data is duplicated, right? Because the data doesn't change that fast. Something like succession, you're not going to see that change every 4 seconds, but we still send the same data every single time. And because of that, it requires a lot of time for us to do manually optimization. When Uber still mostly operate in the US, and our user is on the latest 4G LTE device, then we can get away with something like this. But when Uber grow and we have to support a user base with 2G and 3G device, then really this scheme doesn't cut it anymore. So I mentioned that we did a lot of optimization on ping. One of the optimization that we try is basically try to cut down on the amount of duplicate data that it sends. We did that by calculating the hash on all the data that we shown on the client. And then when we send in the request, we also send in all these hashes. So on the server side, we do the same calculation as usual. But then before we send the data back to the client, we actually check the hashes. So if the hash is different, then we actually send a payload. Otherwise, we don't have to send that particular payload to the client. So this simple scheme actually worked quite well in cut down the amount of duplicated data that we have with ping. Now the problem is that not every data in the app going to be applicable with using this scheme. So something like a nearby vehicle, no nearby cars, it doesn't make sense because you do expect the car to change its position every single time. So something like this really doesn't make sense. But the bigger problem with this scheme is that you hasn't helped with the workload on the server side, right? You cut down on the payload, so the latency is better, it's improved. The client going to get the data sooner. But the workload on the server side keep increasing, and as you have more users, you keep adding more load to the server, and it's at a constant pressure to grow the backend services. So the benefit, like I mentioned, is of course performance. A smaller payload going to lead to a better performance, especially in terms of client networking latency. But the server workload is increasing, and we didn't have that. The first drawback comes in terms of maintenance. So when we fragmented our data like this, then the data come in different time, and if we develop code for such a thing, then we have to have checks all across the application. And when a developer working with such a code, then the mental overhead is really high. So the chances for something wrong to happen is really high as well. The second drawback comes in terms of safety. So at Uber, we try to leverage compiler really heavily, right? So the compiler not only help compile the code, but we leverage compiler in order to do checks and validation for us without having to push code to production to do that. Unfortunately, when you do something like this, then we move all the complicated logic to runtime. So at runtime, then the application is do all the checks and do all the work. Because of that, the compiler cannot help you to do any validation. So this is when we decided to do our first big migration. Right? So at the same time, around this happened, we also moved the Uber backend services from a monolithic backend to a service-oriented architectures. So we break up our backend from a single service, monolithic service, to multiple microservices. Together with doing that, we are also breaking up our API into multiple smaller APIs. So each API now only return a single piece of information to the application. right? So the first one might like return the list of transaction, in the middle return the cars, and the bottom return the feed. You can see that each of the API call can be slower or faster depending on what data that it try to return. And in the example that we just showed, like the feed one might be slower than the other two, and that's totally fine, as long as the application is smart enough that it can render other information without waiting for all the data to come back. Another benefit of this scheme is that you can put different schedule for different API, right? So instead of having the whole world refresh every 4 seconds, now we can refresh the cars every 4 seconds, but transaction of it we can refresh every minute or something like that. And by doing that, we cut down on a lot of the work that we have to do. One note though is, in order to fully taking advantage of such an architectures, you also have to refactor, or you also have to break down the application or UI client as well. Because now each of the UI element has to be able to render itself when it only has the minimal data that it has, right? If the UI code is still monolithic and it requires all the data to come in before it be able to render, then that's not going to work. You wouldn't be able to take full advantage of such an architectures. In terms of benefits, we get back some of the safety that we lost in the previous world, because now we have multiple API, and each API have a really strong schema, really clear what data that is going to return. And because of that, you can be very sure the compiler going to help you in order to that you are doing the right thing. But the biggest benefit that we have from this is that we was able to change the UI code to using reactive programming, right? So the fact is that the UI now doesn't have to worry about request and response like anymore, and then it can think about data in terms of stream, in terms of the reactive programming. So the each UI element is attached to a data stream. So a transaction at the top can be attached or observed on a transaction stream. And whenever the data on that stream change, then it should be able to render itself. So that we call the client contract, right? And that is very important, because once we do that, we was able to do many migration after this without having many changes after this without having to worry about another migration, which is a key of whenever we do a migration. You want to make sure that you don't have to do another migration like 6 months from now or a year from now. The drawback come in terms of simplicity. So of course, when we move to this world, then we lose all the simplicity that we came with Pink. Reactive stream is very powerful. You can combine them, you can transform them any way you want, but when you do that, then it can get really complicated. So the title of the talk is Evolution of Push, but up until this point, I haven't talked anything about push. And in fact, not until we have Ramen that we have the very first push element in the whole architecture at Uber. So at this point, remember that we already went through the transition from a monolithic to service-oriented architecture. So we already break up our backend services into thousands of microservices at this point. Among all of them, so Ramen is a special services. What it does is that is the only service that holds a constant connection to the application. And other services, when it needs to talk to the client, it sends a message to Ramen, right? And then Ramen in turn gonna send this message to the application. So by doing this way, we really abstracted out all the complicated logic of doing a transportation protocol in Ramen. So it have to worry about like connection management, worry about persistence, worry about retry. But all the other thousands of other services really doesn't have to worry about that. They can just focus on the business logic and think about what data that they can send through Ramen itself. Ramen have Ramen itself have two layers. The first layer is basically a priority queue. So every message that's sent to Ramen have two properties. One is a priority, and the other is timeout. The priority determines where in the priority queue that a particular message is going to live, and the timeout determines how long it's going to live in that queue. The second layer is a transportation layer. And in this layer, we'll be able to support like multiple different transportation protocol. We support long polling, we support service and event, we support HTTP2. The idea is that Ramen be able to automatically choose the best transportation protocol to talk to the client. So when you use Ramen, then you don't have to worry about building a reliable transportation protocol because Ramen take care of that for you. What you have to worry about is how to set the priority and how to set a timeout, right? So the timeout can be short or long, and the priority can be low or high. And we do really have data that fit into all the four quadrants of this matrix. So some data like driver GPS, you're going to have a really short timeout because if it passes some certain thresholds, then it doesn't matter for you to see that driver in the last 15 minutes anymore. It have a low priority because we don't want to block other important actions of the user. Now some other messages like a system action, like if you want to send a message to the app and say that it to update itself or it to like backup itself, then you really want to deliver that message eventually, even if the client cannot receive it right now. So you would set a really long timeout to make sure that it's going to be delivered. On the other side, you're going to have message with extremely short timeout but high priority, like an offer. If you send an offer that have expiration to a user, you want to make sure that that offer arrive before the expiration. And the last quadrant is long timeout and high priority, so something like chat messages, right? When you send a chat messages, you want to make sure that the message is going to get there eventually. So we set an extremely high timeout to make sure that happens. Okay, so with Ramen, the biggest thing that we was able to deliver is transport protocol as a service, right? So people don't have to worry about protocol anymore. People don't have to think about how to integrate with protocol anymore. And we abstracted all that out to a special service, and people can leverage that. We hide all the complexity of connection management, persistence, so developer can concentrate and think about the business logic for their own services. And because of that, we have total flexibility in changing underlying protocol. So we have total flexibility to adopt new technologies. So I said that we have 3 different transportation protocols right now. We are also investigating adding gRPC and reactive sockets. The biggest drawback of this thing comes in the fact that we need a migration, right? So a new services is very easy to come on board and use Ramen. But an existing system already built based on like pool model kind of thinking, and then a particular service is like that, but then also the dependency also built like that, then it's very difficult to migrate the entire system to push. And really, if you want to do it, then you have to do it like the entire system at once. We have thousands of microservices. So because of that, we developed another service called Fireball. So what Fireball is a bridge between the pull world and the push world. So all the backend services can still live in the pull model, but the Ramen can live in the push model. And Fireball in between understand both, right? So Fireball can pull data from a backend services and push that to Ramen. And it does that by listening for a bunch of events. So Fireball itself is a rule engine. It can listen for events, and based on this event, then it can query a particular microservices, get the data back, and push that to Ramen. The event can be a server-initiated event. So like when user go on trips, we want to push a new driver information to the app. Or when user has a pull match, then we want to push a new rider information to the app. Or it can be an event coming from the client as well. Like when the user opens the app, then we want to push a session and feed to the app. So the most important thing is that we was able to change the model, right? So before, when you want to think about the architectures, you have to think, OK, I want to integrate with push. So what service I have to integrate with? How do I change my architecture to do that? We change all that. And now the only thing that the developer have to think about is when an event X happens, what data that I have to send, and what priority and what timeout that I have to set, right? So we change all that into a very simple rule model. And when we do this, then we get to a model where we be able to move the entire system in a couple of months from a pull model to push model, right? So now, like the majority of our traffic, up until like 70 to 80% of our traffic actually going through the push model. Another benefit is that we go to a model where we have full control when to send the data. And why is this important? This is important because if you remember the client contract, the client tells you that if you send it some data, then it have to render that on screen. And now when the backend, you have full control over the data. It means that you can build your data, you can build the server in a way that you can change how the client reacts. You can change how the client represent the UI. And because of this, we were able to launch entirely new feature without writing a single line of code on either the server side or the client side. Right? We just have to add new rules or change the set of rules that we were able to launch entirely new features. Once we got this, and we really be able to push this technology across the company really, really fast. Within a few months, people start using, initially for like all the small simple case that I mentioned to you guys about like when the user go online, when the user go on trip and stuff like that, to a lot more fancy and complicated features. This is an example of such a feature. So we actually was able to using this technology to dramatically improve the performance of the application itself. So when you open the app, we can send the smallest bit of data enough to render the application. And the additional bigger data, then we can go through the push channel. And we figure out that when we make the application faster, then more users using our app, and we get more trips out of that as well. We also extend the capability of this channel to do on the background as well. So we'll be able to send data to the user even when they're not opening the app. We do this through support of Google Cloud Messaging and Apple Push Notification. This is an example of a feature that we have in here where people can integrate their Uber app with the calendar so that Uber automatically index all the calendar invite, and we know that when you're most likely to take an Uber to the next calendar event. And when we do that, then we also integrate with background push so that we can prepare all the data that the user is going to need, and then we push the data to the user even before they open the app. So when they open the app, then they're going to have the most optimized experience. Okay, so if one thing I want you to take away from this talk is that there is an importance in terms of having the right contract or the right abstraction, right? So when you have the right abstraction in the framework, in the architectures, in the system, then you can evolve the system without have to worry about painful migration. You can have multiple small changes after you have the right abstraction, and constantly improve the system without having to worry about slow down. But if the abstraction or the contract is too limited, like back when we have ramen, then it's not going to be useful. Not many people will be able to use it. So you have to think really careful about the abstraction. What is the right level of abstraction, and how people can whether it's powerful enough that people can use it. But the most important point is that abstraction is a really powerful, and it's a good thing to have. But it's not free. There is a cost that associated with having abstraction. So I'm very happy that at the beginning of Uber, we have something as simple as ping, so that we can move extremely fast, because otherwise we wouldn't be like the Uber that we have now. So you have to think careful about when to introduce the abstraction as well, right? In the company, if you want to do that in the system, you have to think about when is the right time and what is the right level of abstraction that you should have. So with that, thank you for listening to my talk.